This is Lecture 16, in which we'll discuss at length conic sections. Conic sections refer to three special geometric shapes: the parabola, the ellipse, and the hyperbola. The words themselves are Greek in origin, as are so many things in mathematics. You may understand that there's very few Roman terms, and the reason is the Romans were appliers of mathematics. They used it to build roads, but there was very little mathematics done by anybody who considered himself a Roman. The Greeks continued to work for the Romans, in many cases as slaves, and do their mathematics. But the great mathematics, the theories and the underlying understanding of branches of mathematics was done by the Greeks. And the first person to use these terms to describe these things called conic sections was Apollonius. He wrote a book entitled Conic Sections. Of course, it was in Greek. It was published in 225 BC. So you can see that Apollonius lived about 100 years after the work of Euclid, and was probably one of the latest of the great mathematicians of ancient Greece. He chose the terms from general mathematical terms used by the Pythagoreans. The word parabola was derived from parabole, the Pythagoreans' term for placed beside. Ellipse was derived from ellipsis, which was Greek for deficient or defective. Hyperbola was derived from the word hyperbole, which meant then and means today in excess. Now, to really understand how this deficient, beside, and excess were used for these three shapes, you really need to read a very complicated book of some sort about conic sections. Just let's trust to say that these words were Greek in origin, and they defined three types of shapes and were done by Apollonius. The conic section name was derived from the notion of making these shapes, the ellipse, the parabola, and the hyperbola, by slicing a cone with a plane at different angles. So you can get a hyperbola, you can get a parabola, or you can get an ellipse. And by the way, the cone they're talking about is not our typical cone like an ice cream cone. Imagine an ice cream cone turned upside down without the ice cream in it, and then attached at its vertex another ice cream cone pointing up. That is a true cone. You might call it a double cone. Certainly you wouldn't want to eat ice cream that way unless you were very fast. So a conic section was the name given to these three shapes because they could be formed by slicing or sectioning a cone. Some of the work that Apollonius did on conic sections was available to mathematicians of the 16th and 17th centuries. The first 4 chapters of conic sections was translated into Latin in 1556. This was too late to be used by Nicholas Copernicus, who did a lot of work in terms of astronomy, but he died in 1543, 13 years prior to the discovery and translation of the first 4 chapters of the conic sections text. Chapters 5 through 7 of Apollonius' work were translated into Latin in 1661. This was after the deaths of Kepler and Galileo, again, 2 gentlemen who worked a great deal in the area of astronomy and could have benefited from knowing about the work of Apollonius, since no one else had done it, but it was unknown to them. The last chapter of conic sections, we have no idea what it was about because that was lost and no one has found it, and if we ever do, perhaps we'll learn something that we don't already know. So the great work of Apollonius was eventually discovered and used by mathematicians in Europe, but well after a time when it could have been used by some of the great workers in the area of astronomy. The importance of conic sections became apparent once the idea that bodies like the Earth and the Moon traveled in circles was wrong. There was a gentleman named Ptolemy who came out and said that all of the bodies, the sun, the moon, the planets, etc., went around the Earth in circles. Even Galileo realized that these circles weren't true, but still believed that the circle was the perfect path, and thought that indeed the paths were circular modifications on top of circles. this wasn't right. And of course, Galileo eventually discovered, along with others, that the Earth was not the center of the solar system, but indeed the Sun was, and the Earth traveled in some sort of orbit around the Sun. And it wasn't circular, because when they try to show where the moon would be, perhaps, it wasn't there if you assumed a circular orbit. Now, we now know that depending on the velocity at which an object is launched from Earth, one of three of those conic sections will be its path. An object launched from Earth that does not have enough speed to escape the Earth's gravitational pull at all travels in a parabola. And of course, it returns to Earth because its velocity is insufficient to allow it to escape. An object launched from Earth with a velocity large enough to prevent its return, but not large enough to prevent its total release from the Earth's pull, travels in elliptical orbit as a satellite on Earth. So, for example, we launch a communication satellite or a spy satellite. Any type of the satellites we launch travel in an ellipse around the Earth. And of course, the Earth travels in an ellipse around the Sun. An object launched with enough velocity to totally escape the Earth's gravitational pull travels in a hyperbolic path in space. Our investigation will begin with the ellipse. An ellipse is a shape consisting of points the sum of whose distances from two foci are the same. The foci are indicated by x's on the x-axis inside the ellipse you see pictured. The distance from the center of the ellipse to each focus is labeled C. Okay? The distance from the center to each vertex on the major or longer axis is labeled A. And you notice on the graph we see A on the x-axis and negative A. That is the longer axis for that ellipse, and therefore it is along the x-axis is a horizontal ellipse. The distance from the center of the ellipse to each vertex or turning point on the minor or shorter axis is labeled B. And you see in your picture you have a point B and a point negative B on the y-axis. Thus, the y-axis is the minor axis for this ellipse. Now, for any ellipse, A squared equals B squared plus C squared. A little different than the Pythagorean theorem. A being the distance to the major axis is the longest distance, and A squared equals B squared plus C squared. We now examine the general equation for the ellipse whose center is at the origin. Remember, the origin is at 0, 0. That is the type of ellipse pictured in our graphic. If the major axis is along the x-axis, then we have an equation, x squared over A squared plus y squared over B squared equals 1. If the major axis is vertical, it's the y-axis, then we have x squared over B squared plus y squared over A squared equals 1. Remember that A is bigger than B, so that by looking simply at the equation of this form, if the number underneath the x squared is larger, then the horizontal nature is the nature of this ellipse. If the number under the y squared is the larger of the two denominators, then the ellipse is oriented up and down along the y-axis. If A and B are equal, then the ellipse collapses into a circle, and the two foci become the center. So a circle really is a very special form of ellipse. And it turns out that many of the orbits in space are almost circles. Not quite. They're ellipses where the foci are very close together and therefore almost at the center of the ellipse. The major use of the ellipse is to trace the path of a satellite. Using Tycho Brahe's data on planetary positions, Kepler was able to state the paths of the planets. And this is a very interesting story. Tycho Brahe was a Danish mathematician and scientist. And it's not easy to obtain from the picture, but he actually had a metal tip on his nose. part of his nose was cut off in a duel. And he obviously didn't want people to see that missing part, so he put a piece of metal for the tip of his nose. And Brahe worked for the Danish king, and this was before telescopes used observation of various planets made with himself and his assistants working for hours and hours throughout the years until they had very specific sets of data on the location of Mars and Mercury and Venus, the visible planets at that time, at any particular date and time. But Brahe was a strange man. He was unwilling to release his data to Kepler, Johannes Kepler, who was working on the paths of planets, because he felt that if he gave his data to Kepler, Kepler would get credit and not Brahe. Well, what happened was Kepler and Brahe were both invited to come to Prague, which was then the seat of the Holy Roman Empire. The emperor at the time wanted to make the Holy Roman Empire a seat of scholarly work, and therefore invited the great scientists and mathematicians to come to Prague and to work under his payment, if you will. And when they discovered things, the knowledge would be centered in the Holy Roman Empire, giving him a great deal of credit. So Brahe came with his data, but still refused to give it to Kepler. And Kepler said, okay, tell you what, would you give me one set of data, just the data on Mars? And Brahe figured, okay, I'll do that, whet his appetite, and they'll come begging to me and guarantee me credit if I give him the rest of the planetary data. So he did. And Kepler took the data on Mars, recognized what had to be done, and while in Prague, wrote his laws of planetary motion, gave the data back to Brahe and said, thank you very much. And Brahe asked, do you want the rest of them? And Kepler said, I don't need it. And Brahe never got credit. It's Kepler's laws of planetary motion, which goes to prove that perhaps you can be too egocentric and have a real problem. In fact, Brahe died in a very painful way because he was egocentric. He was at a banquet, and if you'll excuse the expression, needed to use the lavatory, but refused to get up because he didn't want to bring attention to himself as being rude, because he wanted people to think that he was a wonderful fellow. And he died of internal poisoning at the banquet. Meanwhile, Kepler, using the data and his own knowledge of ellipses, came up with his rules of motion of planets. And one of his rules was that planets travel about the sun in an elliptical orbit. And basically, the moon would travel around the Earth, or the moons of any other planet would travel around their planet in an ellipse. The elliptical orbits were to be expected for any body traveling around a heavier body, like the Earth around the sun. In the latter half of the 20th century, we began to place artificial satellites in orbits around the Earth. These orbits are all ellipses, and we still need to know about Kepler's laws to be sure to place the ellipses in the right orbit. For example, there are, I said ellipses, we need to place the satellites in the correct orbit. For example, there are satellites that are called geosynchronous. That means that satellite is above the same point on the Earth. It travels around in an ellipse, but as it travels, the Earth is spinning. So the location under which the satellite is located is always the same. We need to know where that ellipse is for that orbit. In fact, if you have one of those satellite dishes, it always points at the same location because you have a satellite that is traveling in an ellipse in a geosynchronous orbit. Without the mathematics of ellipses, we could not do that. Next, we will examine the parabola. We've already seen the parabola in our discussion of the quadratic polynomial function. A parabola consists of points whose distance from a focus located inside the parabola is equal to the perpendicular distance to a directrix located outside the parabola. And in the graphic, you can see the focus marked with an X. You can see points on the parabola, and you can see the directrix. Any point on that parabola has an equal distance from the X, from the focus, and a perpendicular distance to the directrix. The vertical parabola, the kind pictured here and the kind we looked at in quadratics, has a vertex located at HK, And we have the general equation y equals a parentheses x minus h squared plus k. If the parabola is oriented to the left or to the right, it has an equation x equals a parentheses y minus k squared plus h. hk is still the x and y coordinates of the vertex. The parabolic shape has many uses, but one use we've already referenced, and that is the use of the ballistic trajectory. But because any body traveling in free fall, where the only force acting upon it is gravity, travels in a parabola. This is true for a ballistic nose cone, once the engine is turned off, a kicked or thrown ball, a bullet fired from a gun, an arrow fired from a bow, or any other form of object that is launched with an initial velocity or even dropped, and the only force acting upon it is in the gravitational field of the Earth. Now, obviously, if the object is dropped, it will travel in a straight line down to the Earth unless the wind blows it. But if you look at a function of its location over time, distance from the Earth over time, that will be a parabola. So a parabola is involved in all of these ballistic paths. A three-dimensional parabola, called a paraboloid, is quite significant in modern society because the paraboloid reflects all the rays from a distant signal, a signal that could be a radio signal, a radar signal, even a set of light coming in from a far distance will be reflected to the focus of that paraboloid. Thus, we use a paraboloid for reflecting dishes. That is, the dish surrounding the antenna for a microwave, for a relay station, is a paraboloid. In fact, we use it for radio antennas that seek out radio signals from outer space that might give indications of intelligent life. When people talk about the antennas, they really are talking about the reflecting dishes around the antenna, and those are generally paraboloids. In 1100, Omar Khayyam used parabolas to obtain solutions to specific cubic equations. Remember, we mentioned in an earlier lecture that people were trying to come up with a general solution to the cubic, and Khayyam was able to do some, but not all. Omar Khayyam, by the way, again is known primarily as a poet, in which he was. He was a great poet. And he also was a rug maker, because we talk about Omar the rug maker, or the tent maker. But basically, his mind was mathematical. And he did a great deal of work using geometry, and therefore including using the parabola, to solve problems. He was also used mathematics to design calendars and to try to update the calendar to make it correct. Because calendars, as you must understand, in those days were primarily used for two functions: religious holidays and agricultural use. They went to plant and those kind of things, as well as went to celebrate certain holidays. And the Muslim faith was concerned about the celebration of their holidays. And Khayyam worked using mathematics to try to figure out exactly what one year was, because people didn't know. And in fact, in Europe, it wasn't until the late 16th century when the Gregorian calendar was created, and we got somewhat more accurate than the Julian calendar, which by the time 1580 rolled around had lost about 10 days. So Khayyam was a man of many talents, but his talents were all based, it appeared, on mathematics. And he did use a great deal of geometry, which probably indicated why he became involved in making things, because they were geometric shapes in terms of tents and carpets. Our last conic section is the hyperbola. Okay? And an hyperbola, or a hyperbola, I'm not really sure which way to say it, they both sound incorrect, is a set of points where the difference between the distance from each point and the two foci is constant. The difference rather than the sum. An hyperbola is comprised of two parts that are symmetric. And we can see in our diagram we have the two parts of the hyperbola. The foci are indicated with X. The center is at the origin. And we have axes that sort of act as axes of symmetry. The y-axis is between the two parts of the hyperbola, and the x-axis cuts the two hyperbola parts right in the middle. You'll notice there are some dashed lines. Those dashed lines are asymptotes, that is, the ones that are slanted. The hyperbola gets closer and closer to those dashed lines, but never touches them. And those asymptotes are the diagonals of a rectangle formed by the values of a and b that we'll see in the equation. Notice that here, c squared, which is the distance from the center to each of the two foci, is equal to a squared plus b squared, similar to the notation for the Pythagorean theorem. Okay, the diagonals of those rectangles, again, are the asymptotes, and the distance from the center to the focus is c. The distance from the center to the vertex is labeled a, and that is the actual place where the two parts of the hyperbola cross, in this case, the x-axis. Those are the two vertices. That is labeled a. And b is the distance from the center to the top and bottom of that rectangle. Now, the question is, how do we recognize an equation of an hyperbola? Well, we notice that we have three equations on the graphic. The first is x squared minus a squared, x squared divided by a squared minus y squared over b squared equals 1. This is an hyperbola oriented along the x-axis, okay, because y can be 0, but x cannot be 0. If x is 0, you have a negative square fraction equal to a positive 1, which it cannot be. So this first equation is the equation of a hyperbola that is oriented horizontally. It has an x-axis that cuts through it. The second one, notice the negative is between the y squared over a squared and the x squared over b squared, is the equation of a hyperbola oriented vertically, up and down the y-axis. Because in this particular case, y cannot be 0. And a is always the square number underneath the major axis. In this case, a squared is under y squared. A can be greater than b, or a can be less than b, or a can be equal to b. It's irrelevant. C, the distance from the center to the focus, is indeed the largest of the three measurements. Notice there's a third equation that looks a bit different. This is xy equals k, where k is a constant. This is another form of hyperbola. This is a hyperbola generally that falls in the first and third or the second and fourth quadrants, depending whether k is positive or k is negative. Because if k is positive, x and y must both be positive or both be negative, and therefore the two parts of the hyperbola will lie in the first quadrant where x and y are both positive, or in the third quadrant where x and y are both negative. If k is a negative number, then x and y must be of opposite sign, which is found in the second and fourth quadrant. Okay. The hyperbola does not have as many applications as the ellipse or the parabola. But there's one very interesting use of the hyperbola, and that is LORAN, long-range navigation, which is used to navigate over water. Having been through the Air Force Navigator School, I used LORAN very successfully to navigate across part of the Pacific Ocean, and it was very accurate. And suffice it to say, the way hyperbolas are used is that different radio stations are set at different frequencies, and once you identify a particular radio station, you get a reading. And then you look on your map of the water area, the Pacific Ocean, and you see hyperbolas of a particular color. Each colored set of hyperbolas is related to a specific frequency radio station. So let's say the radio station you are tuned to, which is putting out a signal, is related to the purple hyperbolas. You look at the purple hyperbolas, they are labeled with numbers. You find the hyperbola that has the number you read off your LORAN set, and you are someplace on that vast hyperbola. You're not finished yet. Then you tune to a different station, and perhaps those hyperbolas for that station are green. You find the green hyperbola that has the number that is read on your set. And then you tune to a third station. Perhaps it has red hyperbolas. And you see the red hyperbola on your map that has the same number. You now have a location on three hyperbolas. Hopefully they're pretty close. Ideally, they are the same place. They're a place where the three hyperbolas identified intersect. but generally they meet in a very small triangle, and you approximate your location at the center of that triangle. Another use of the hyperbola is the three-dimensional hyperboloid, which is the shape of the cooling towers at nuclear power stations. The one area where hyperbolas are used and are quite common is in that xy equals k hyperbola, because the graphic representation can be used in something called indirect variation. Indirect variation is used in relationships where as one thing increases, the other must decrease. A good example of this is the frequency and wavelength of a wave, a light wave, a sound wave, a radio wave. As the frequency increases, the wavelength decreases. That is, the wavelength, which is symbol Greek letter lambda, and the frequency, letter f, equal the speed of light, c. So lambda times f must always equal c if you're dealing with light or things like radio waves. For sound waves, lambda times f would equal the speed of sound for that particular medium in which you're working. Why is this important? Well, for example, did you ever notice that if you're old enough to remember we had TV antennas, that the original TV antennas were quite large? Because those were VHF, very high frequencies, which weren't near as high as UHF frequencies, which were used for the UHF stations that were added on later. We needed more stations to watch more football games on Saturday. Now, those antennas for the UHF stations were a lot smaller. Why were they smaller? Because the length of an antenna is based on the wavelength of the wave you're trying to capture. Since the frequency went up, the wavelength went down. And as frequencies get higher, wavelengths get smaller. If you look at the antenna for like a low frequency radio station, that antenna is huge because small frequency, large wavelength. Another use of indirect variation is something, for example, where we have the pressure and volume of a gas are indirectly related if you hold the temperature constant. The equation is PV equals nRT. N and R are constants, and if the temperature is constant, we have PV equals K. That is an hyperbola. And therefore, we need to know about hyperbolas to graphically model the relationship between the volume and the pressure of a gaseous substance. One very interesting use of all this material was discovered by Edmund Halley. Edmund Halley was a friend of Isaac Newton. In fact, I mentioned in an earlier lecture that he was the one who forced Newton to publish his book on fluxions, because Newton refused to publish it and only shared it with his closest friends, which included Halley. Halley, in 1704, examined the path of a comet, which happened to pass by. That comet, of course, has returned about every 75 years in a very predictable date, and of course is known as Halley's Comet. I am told that Mark Twain was supposedly born under Halley's Comet and died under Halley's Comet. Whether that's true or not, it sounds like Mark Twain. And what Halley came up with was a way to predict the shape of a comet. That is, would the comet travel in a parabola, an ellipse, or an hyperbola? Let's see what he did and why it's important. First of all, he required to know the comet's velocity, and then in the formula had three other variables or constants. One was capital G, which is the gravitational constant. M is the mass of the sun, and P is used for the distance from the body to the sun. That is, the body being the comet. V is the velocity of the comet at its vertex. And now we see a set of conditions that must be met to get the various shapes. If V is less than the square root of 2gm over P, we have an ellipse. If V, the velocity, is equal to that square root, we have a parabola. If V exceeds the square root, we have a hyperbola. The important thing here is only if the velocity indicates an ellipse will we see a comet more than once. So that takes care of conic sections and the comets. Our next lecture, we'll begin a series of lectures on probability.